So I'll talk to you today about the SWOT mission, and in particular what we're going to do in the future for fine resolution sea surface height with SWOT and its links to surface currents. And I'd just like to acknowledge, because he's here in the audience, Ernesto Rodriguez, because the SWOT mission, a lot of its technical scientific development is thanks to him over the decades. And also the extended SWOT science and project teams. So SWOT is bringing together two communities, the surface water community with hydrology and the ocean topography community. The hydrologists are mostly concerned with measuring elevation levels over lakes, rivers, floodplains, and they have with the intention of looking at the global budgets of water storage and also river discharge on these different timescales. I'm going to be talking today mainly about the ocean objectives, and for the oceanographers, the objective is really to try and have a better observation of the smaller mesoscale and perhaps some of the larger submesoscales. And today's altimetry maps only really resolve down to about 200 kilometres in wavelength, so the larger mesoscales. And so there's this missing gap between what will resolve with SWOT, it's about 15 kilometres, and 200 kilometres, which is really neat to understand the ocean circulation and for climate studies. The second thing for SWOT is that it is tuned to have a good observation of the ocean tides, and so that is also important for the ocean's energy budget for mixing and eventually the pathway to dissipation. And it also has a technological objective because it will set a new standard for what we can do with wide SWOT altimetry in the future. So the SWOT measurement concept, it's using, it has a nadar altimeter in the middle. It has a 10-metre baseline with two interferometric antennas either side. And the radar impulse is sent down by one, received back by the other, and then we measure the difference in range and also in phase to then use interferometric techniques and get a cross-track resolution that ranges from about 70 metres close to the centre to around 10 metres at the exterior. These sea surface height observations are also with very low noise. They will be roughly or more than an order of magnitude lower noise than we have with conventional altimetry today. But very high resolution observations, it's impossible to download that over the whole globe. So the decision was made to have very high resolution over the surface waters where we really need it, and to do some of the main steps of the interferometric processing on board. And we'll download over the global oceans a low resolution product, which is 2 kilometres, the basic grid, with full corrections, wind waves, etc. at that 2 kilometre resolution. And then there's an expert high resolution product, which will be at 250 metre resolution, and including some SAR images of power variance, Doppler centroid, also at 250 metre resolution. So I was very glad to have a lot of the descriptive of cross-track interferometry explained earlier. But essentially, we receive back at the two antennas the raw images. There's SAR processing that will be done on board for the ocean products to give us focused images, and then interferometric processing also on board to give us amplitude phase coherence. And then the onboard low resolution products will be downloaded, and the geolocation, different calculations, etc. will be done on ground. For the high resolution over the lakes, terrestrial surface areas, most of the ground processing of the interferometric processing will be done on the ground. So just to give you some idea where this will happen, this is currently the mask we're going to use, where we will download the high resolution data in red, and the low resolution data will be available globally, so over the whole continents as well as the oceans and the sea ice up to 78 degrees north and south. So SWOT will have 2 orbits. During the first 6 months, we're in what we call the fast sampling phase. So the first part of that will be for instrumental checkout and some of the engineering calculations. The second 3 months of that period will be for science studies, and in particular for looking at small, rapidly evolving ocean movements. And then we move into the 3-year nominal phase, the science mission, which will have a 21-day repeat. This is so that the hydrologists, our partners, will have measurements over the smallest lakes and rivers, even at the equator. So we needed 21 days with our 150-kilometre wide swath to cover all of those equatorial zones. But the oceanographers had asked that we have subcycles that are better adapted for ocean observations, and so we have a subcycle like the 1-day mission at the top. And then after 3 days, we get this sort of coverage. After 10 days, we've covered the whole globe, but you can see there are small gaps between the tracks. And then the second 10 days of the 21-day phase, the whole thing shifts westward, and we fill in all of those small gaps. But essentially, after 10 days, we cover all the globe. But you can see that there are different latitudes where, especially at high latitude, where we're getting 4 to 5 coverages per 21-day cycle. So our basic ocean science objectives, as I said, the main objective is to better understand the smaller mesoscales and the submesoscales. So this is a plot from Jim McWilliams' review paper, where you can see, using sunglint data, these swirls at the surface of the ocean. These vortices have a 5-kilometre radius, and in the SWOT community, we talk always about wavelength. So wavelength is a Fourier wavelength, 5-kilometre radius, it's a 10-kilometre wide diameter, and it's a 20-kilometre resolution, spectral resolution. So this is the sort of things we should be able to observe with SWOT, depending on wave conditions, etc. Another big thing that we are interested in is that we've talked a lot about these Aviso maps resolving the 200-kilometre wavelength scales, and this is from Chelton's work using eddy tracking algorithms to look at cyclones and anticyclones. But you see, for example, in the North Atlantic, that these big eddies, they just spontaneously appear in the middle of the ocean, and then they spontaneously disappear. Of course, that's not happening, but all of the small-scale structures that feed into the large-scale eddies, we are not capturing with today's altimetry. And with SWOT, we're hoping to have a much better idea of these important generation and dissipation phases. And of course, we've seen that there's a lot of very high-resolution numerical models, and we really need observations to validate if the physics that they're representing matches reality. So this is an example of one of these models showing submesoscales in the Kuroshio area in winter and in summer. This is relative vorticity, which is the second derivative of sea surface height. And here we have the vertical velocities in this box for the same time period. And you can really see these columns associated with the small submesoscales in winter. You get these columns of vertical velocities going up and down, and changing the density, changing the uptake of heat, carbon, etc. Very important. And here the bottom of the mixed layer, you can see that there are also submesoscales that are injecting in below the mixed layer. In summer, we're dominated more by the larger mesoscales, and you can see that there's very little activity in the very shallow summer mixed layer, but most of the vertical velocities are coming from the deeper reaching dynamics. And the one thing with sea surface height is that it measures the vertical integral of these density or pressure anomalies at depth. And so these deep-reaching structures are really what's going to be reflected most clearly in sea surface height. And we should be able to measure a lot of these small submesoscales in sea surface height in winter, and in summer, probably more of these deep-reaching mesoscale structures. And And so today we are already starting to measure that from models, but also, as the last example showed, but also in situ data. This is measurements of kinetic energy spectra, not sea surface height, but kinetic energy here in the Gulf Stream. And in summer, you have relatively steep slopes in wave number spectra, more energetic here at large wave numbers, less energetic here. Whereas in winter, we had all of these small scale submesoscales. It bumps up the energy at small scales, and the slopes are shallower. So today's a long track altimetry. We're starting to get a bit more precise in the way we're analysing a long track altimetry and processing the data. And we're starting to be able to see, for example, in summer, that the spectral slopes here are steep, and in winter, they're shallower. So we're starting to be able to pick that up in a spectral sense with these one-dimensional cuts through this turbulent field. We really need to understand how that's also evolving in terms of the anisotropic structure of the mesoscales and the submesoscales, and the strain and the regions of convergence in these areas surrounding the eddies. So that's all part of the objectives for SWOT. So this is just to give some idea. We have confidence that we will be able to measure it because we can already see some of it with a long track data, but we'll be able to measure it much more finely with SWOT. Another thing in terms of the relation between what's happening at the very surface layer and what sea surface height is reflecting as the integrated view. This is an example of the fact that altimetric sea surface height gradients respond to the depth integrated flow. So this is a section in the Southern Ocean going across a very strong front with a small eddy. And in black is the sort of equivalent sea surface height. You see these strong sea surface height gradients lining up with the fronts. And altimetry is responding to this depth integrated view. But if you look at the sea surface salinity, you can see that there is actually sea surface salinity, low salinity being pushed north of the fronts in the Ekman layer. And so there's actually small fronts associated with the north of that, with each side of the eddy. And so there's a lot of detail in the surface fronts and the surface currents that may be shallow and it may be deep. So it's very, all this preparation for the surface current missions, it's really useful to be able to combine the very detailed look of what's happening at the surface with altimetric sea surface slopes that give you what would be a depth integrated and perhaps more intensity at depth. So in terms of reconstruction, this is some work that was done by Lucie Gauthier a few years ago, taking a very high resolution numerical model of California. This is the sea surface height, so it doesn't look as high resolution as what you've seen for traces or for currents, but the gradients associated with that drive these very complex currents that we've been seeing all this morning. If you just take a long track sampling through this and map it using scales like we do with DUAC's Aviso maps today, you get this kind of smoothed image, which isn't too far, but the currents derived from that are much smoother and much weaker and losing a lot of details. So SWOT will measure, it's not just the nadar measurements, but you've got measurements over the 150 kilometres. As I said, it comes back within a 10-day period, covering more of the zone than you have with nadar altimetry, and the representation of the currents is much closer. So even though we're measuring sea surface height, which is a relatively smooth field, it's the anisotropy, the gradients of that sea surface height that are going to be so important for measuring any surface currents or geostrophic currents. So the second major objective for SWOT is that we aim to have a much better measure of the tides, and this is at the most a great opportunity but also a challenge. The SWOT orbit was chosen to be non-sun synchronous, which is a huge hassle for the engineers, but it's pushed by the science community. and it will also resolve over the 3-year period the main tidal constituents. And I'd just like to say this is the first wide swath mission that will have that as a major objective, and it may be the last, because I think all of the other ones being planned in the future are all sun-synchronous, so they don't resolve the full range of tidal constituents. So this is our current knowledge of a comparison of different state-of-the-art tidal models, and where it's white, they all agree, so we have and they agree with in situ observations. So essentially where we've had Topex JSON data for a long period, we have very good estimations of the barotropic tides, but JSON does not give us good resolution in the coasts, nor north or south of 66 degrees. So we have a lot of errors in our barotropic tides in these coastal and high latitude areas. And where the barotropic tides interact with bathymetry in a stratified ocean, you get internal tides. And that is something that models predict, and we have some idea of their two-dimensional propagation, but we don't have at the moment we can measure this with a long track altimetry just in one direction, but not the full two-dimensional propagation. So SWOT, with its two-dimensional coverage, repeated on a cycle that will resolve the coherent internal tides and the barotropic tides, will give us a very large improvement. So one of the things with the internal tides is that they're generated regularly, but this is an example from an analytical model where they're generating internal tides here at the bottom boundary and propagating it up through either a zonal current with low turbulence or a zonal current with a very turbulent field. And you can see that here the tidal signal is perturbed but essentially passes through the current. And so you can imagine you can do harmonic analysis either side and you get a good representation of the internal tide. In this case, it gets completely shattered by the interaction with the turbulent current. And so this is what we call an incoherent or non-phase locked tide. And it adds a lot of very small scale energy into the ocean at the same time that we have this mesoscale energy from the current. So the current is really completely destabilising the tide, but the tides are also coming in every 12 hours, hitting the current on the side and destabilising some of the mesoscale eddies. So this interaction between the internal tide and the mesoscale field, how it leads to extra instabilities, how it may lead eventually to mixing and extra dissipation is something that we will observe the surface features with SWOT, and we're hoping that the whole community advances on modelling and understanding these interactions. And so just to reinforce the point that SWOT, I've said we will download 2-kilometre resolution data, but also 250-metre data, so in the coastal zones or in the sea ice or in areas where we need more resolution, we can come back to this slightly noisier but much finer resolution data. And this is example of tidal currents with a model, and at the moment we can only validate them using a long track altimetry which is widely spaced, or tide gauges which are also very widely spaced. SWOT will be the equivalent of a 250-metre resolution tide gauge everywhere and allow us to have better estimations of currents. So that will help for SWOT, but will help also if we've improved the models for all the past missions and for all your future missions looking at surface currents with other technology. The tides, I think, from SWOT will be a real game changer. I'll finish. Yep. So just to say that CalVal is also part of the SWOT plan, and in particular, during this fast sampling phase, we're already talking about a lot of studies to try and understand the pressure field and the three-dimensional currents and how they reflect in sea surface height. And we're discussing with the S-mode campaign and different campaigns to perhaps try and do that with this one-day repeat of having very high resolution sea surface height every day. So I won't talk about this, but just to say, like all altimeters, We will also improve the marine gravity field. We will go to 78 degrees so we can possibly measure the sea ice and the polynyas between the sea ice to look at freeboard and eventually ice thickness, and polarized caps. So, SWOT and surface currents. We really need careful processing to remove noise and ways of removing coherent internal tides to then try and analyse the sea surface height and eventually sea surface height gradients for balanced motions. We're really aiming to have a much better idea of the anisotropic structure of these eddies than what we have with the gridded maps today. I've talked about the fact that we can that the balanced flow reflects what's happening in a depth integrated sense, and it's very complementary then to any of the surface current missions that we've been discussing this morning. I've talked about tides, and in particular one of the things that's very exciting for our community is to look at this interaction between the internal tides and the mesoscale and small mesoscale fields to understand their dynamical interactions. And I'll just end by saying that SWOT's measuring using SAR interferometry, and we are going to renew the science team. There'll be a call in February 2019 to have a science team that goes up to the launch, and renewed science team. So please, if you have any interest in joining us for the SWOT team, contact me or any of the other people involved in SWOT. Thank you for your attention.